So as to your second question, which was not related to this, do you know if the handbook has an interpolation equation? I haven't seen one, so I think the answer is no. But even if there was, I wouldn't recommend looking for an equation to interpolate. I think the best thing I can do for you here is to give you a technique for interpolating and how to understand it in a way that you can do it quickly and confidently so that it's just not an issue for you at all. Not to say that there's anything wrong with using an equation, but I think you spend half the time with any equation trying to figure out what each parameter is and how that applies to your specific situation. And that's where the mistakes will end up being made. So I'd say, heck with an equation. Let's just understand the fundamentals and understand them deeply so that you can quickly and confidently interpolate when you need to. So let's just make up a little example about this. Let's say we have a curve, and I'll give you the equation of the curve. This is kind of a mathy way to look at it, but you can use this for basically any table of values. So let's say you had something like y equals x squared, and we'll just do the positive domain. So you can make a table of values from that. You could say some values of x, some values of y, and I'll just pick a few values for x, 1, 2, 3, 4. Then y would be 1, 4, 9, 16. And then we could draw that on a graph if we wanted to. And we could plot those points, 1, 1, 2, 4, 3, 9, 4, 16, etc. And then let's suppose I came along, well, actually, so we generated this table of values from a known curve, which was defined. So if I wanted to know what the y value is for some intermediate x point, like let's say I wanted to know if x is 3.3, what is y? Well, that's easy. You're just going to grab your calculator and square 3.3. And whatever that number is, you'll report it and we'll be done. But let's say you had the table of values, but you did not have the equation of the curve, couldn't do the same thing. So you'd be stuck with a graphical option, like drawing a line connecting those 2 points, 3, 9 and 4, 16, and then finding a point that's 30% farther than 3. And doing that graphically is just super messy, so you wouldn't want to do it. Interpolating is a more rigorous way of doing it, but it's worth noting that it's not perfect because this isn't a line, it's a curve. So if I find a point that's 30% of the way up that line, it's not on the curve. It's a little bit to the left. So for this particular shape, I would be understating the value. But that's okay if we know a value that's close enough to the point that we're interested in. If we know 3 and we know 4, 3.3 is close enough in the middle. I think it's just worth noting that interpolating is imperfect, but it's good enough for our purposes, and we're going to use it over and over again. So how do you set that up? Well, I like to make a mini table of values just using the ones that are going to be involved in our calculation and the one that we want to know. So let's recreate that and say x and y. When x is 3, y is 9. When x is 4, y is 16. When x is 3.3, then our variable, I don't want to use x because that's going to create confusion, so I'll use n. So what's going to be the value of n? I want to do 3.3, not 3.1. So now how do you set this up? Well, it's basically a ratio. It's the difference between these two as compared to the total difference for the x values equals the difference between these two as compared to the total difference for the y values. So then we could say 3.3 minus 3 over 4 minus 3, the total distance. And I said distance, I meant difference, but actually distance is a good way to think about it because it ties back to this graphical model. It's the distance from 3 to 4. So 4 minus 3 is the total. And then for the y, it's going to be n minus 9 over 16 minus 9. And now you have an algebra problem. and I won't bore you with the details there. I'm sure you can work that out. But n turns out to be 11.1. And if we come back to our original equation, do 3.3 squared, it is in fact 11.1. So we know we're good. And, is that an equation? I leave it to you if that's an equation. I see it as, the difference of these two over the total distance as compared to, right? That proportion, that ratio has to be equal to the same for the y values because it's a line. When we say interpolating, it's linear interpolation because there's a working assumption that what's connecting 2 points is a line. That's like a deeply embedded assumption that's not often stated, but is in fact what we're doing when we do linear interpolation. Just one more point on this before I leave it. If you ever want to kind of do it your own way because you see it differently than what I've just described here, and you see a shortcut, then absolutely take it. And I'll give you maybe a simple example and then a more complex one. Let's say it's halfway. Let's say it's 3.5. Then you may say, well, I'm then just going to take the average of the y values. That's absolutely fine. I would do the same thing. Even something like 3.3, you might say, well, it's not halfway, so I got to do the formula. Well, maybe you don't. You could say that's 30% of more than 3. So whatever the distance is between 9 and 16, what is 30% of that? Well, 16 minus 9 is 7. 30% of 7 is 2.1. So just tack on an additional 2.1 on top of the starting point for the y value, which is 9. So 9 and 2.1 would be 11.1. I almost confused myself there. But the point being is that if you see a shorter way, don't be afraid to take it. There's nothing so strict about this that you have to worry about formulas. Basically, you're checking yourself as you go. You're sort of, even just now when I sort of got confused, it's like, well, what would be reasonable here? It's got to be between 9 and 16. How far between 9 and 16? Well, a little less than a third of the way, more than 9, 30% of that total distance tacked onto 9. So I won't belabor that any further, but hopefully that's helpful.